last segment. We've already looked at a thin spherical lens. We had an optical axis. We put a lens that had convex curvature on both sides. In the path of some parallel rays. And we found that they focused to a point. We called that the focal length. Fantastic. Okay. We found that the convex mirror is the nice one. Nice in the sense that wherever we put the object, doesn't matter. We always get the same kind of image, the same kind of way. However, it's for a concave lens that we get that kind of behavior. We call this maybe not a concave lens necessarily, but a diverging lens. The rays that come in refract inside, and then it's all like they refract a little bit inside, and then they hit this boundary, and they have the same kind of angle that they did. You draw it this way. An incoming ray that is parallel to the optical axis has a small little jog of refraction here. We approximate that by saying that it continues to the middle and then bends such that it goes through the focal point. Just like a mirror. Except for a concave mirror, the focal length was on the mirror side of the lens. We expect the light to come in and keep going. We just expect it to bend. I expect a focal length over here because I expect the light to make it through the lens. For a concave or diverging lens, it doesn't do that. And so just like for a convex mirror, we have to put the focal length on the wrong side of the optical instrument. For a convex mirror, we had to put the focal length on the other side, the side where the light doesn't reach. Here, we have to put the light on the side that we don't expect. We have to put the focal point on the side that we expect the light to be moving away from. Again, it's backwards. A diverging lens has a negative focal length because it's on the wrong side. We expect transmission, not to bounce back. So we draw through this focal point. Same story, otherwise a ray through the focal point leaves parallel. We can't draw the ray through the radius of curvature because it's not going to bounce back. So what's the third ray that we draw for a lens? The answer is we don't really need a third one, just like we didn't really need a third one for other ray diagrams we drew for mirrors. Where does it look? If we're over here, because this is where we expect to be able to see the image of the object. We expect the light to propagate through the thing and get to our eyes. If we're over here looking at these rays, well, they're diverging, but our brain says, okay, it looks like they came from over here. Wait a minute. This ain't right. Concave? Yes. Diverging. This is a diverging lens. We expect a ray coming in to bend away. It's not this. Oh. I gotta change this. A ray through this focal point hits the lens and bends away that way. I don't want to have to keep track of that. There's nothing to draw it through. That's what should have happened. So what do we draw instead? We've got two choices. The nicer one is to draw a ray through the very center of the lens itself, where these two surfaces are just about parallel and the total resulting refraction is minimum. It just passes through the center here, unchanged. Okay, if we're on that side, we look back this way. Where does it look like they met? Here. The other option is to imagine a ray. Let me use a third color here. The other option is to imagine a ray leaving this object and going to that focal point. The focal point on the proper side of the lens, the transmission side of the lens. Going through the focal point, leaves parallel. Bends away from the direction it's going. If we back cast that we end up at the same spot, and we say that the image is here. Smaller, upright, and virtual. No light rays actually intersect there. It only looks like they do. The red ray actually does pass that point, but there's nothing else to intersect with, so it just keeps going. It only looks like the rays intersect there. Notice that smaller, upright, and virtual is exactly the same classification we had for a convex mirror. A diverging mirror, right? We hit the mirror and the rays bounce off away from that optical axis, and we extrapolate them back behind the mirror to that point back there where it looks like they came from. That mirror diverges the rays, this lens diverges the rays, and we have the same behavior. It's pretty cool. This answer doesn't depend on where we put the thing. Okay, so wait. So if a diverging mirror, convex, and a diverging lens, concave, have the same behavior, then do I expect a converging mirror, concave, incoming rays are focused to a point, to have the same behavior as a converging lens, which had better be convex? The answer is yes. Everything we said for a concave converging mirror is true for a converging lens. Just a converging lens is convex. Since everything we said is basically the same, we could do some geometry. And in fact, I think the textbook does do some geometry. So if you're curious about the geometrical proof of the following, check out the textbook. We have the same equation, true for mirrors and lenses, which makes sense in a way. We're just trading transmission refraction for reflection. We just have to change the convention a little bit. Our assumption is that the object distance is positive. It's on the object side of the source side of the lens. We expect an image to be on the other side. We expect the image to propagate through the lens and get to this side. If the image is on the transmission side, let's let that distance be positive. If the image ends up on the same side, the source side of the lens, let's let it be negative. Note that that's the backwards convention from mirrors. For mirrors, we expect the light to hit the mirror and bounce. So when it's on the same side, we call it positive. But for lenses, we expect it to hit the lens and keep going. So positive is on the other side of the lens from the object. Same story with the focal length. We expect it to focus on that side if we're caring about a focus on this side when it's a negative focal length. This equation is the same, then the equation for magnification is probably the same also. Hi over HO. And again, if the object is inverted, is upside down, then this HI is negative. So we could have negative magnification and positive magnification just as well. If the absolute value is bigger than 1, then it has been magnified. It just might also be flipped around. If we relate this and this, we can show that this is negative . And the reason for that negative sign has to do with the conventions that we choose. HI is negative when it's inverted. For a lens, just really quick, that's inverted, but it's on the correct side. HI over HO is going to be negative. DI is positive though, because it's on the transmission side of the lens. DO is assumed positive, so this quantity is positive. In order to make it negative so that it lines up with this, we have to include the minus sign. The same conclusion works for mirrors, and the same minus sign applies. We just had to reverse, like I said, reverse the convention because we're talking about reflecting the reflection, the reflective side of the mirror as opposed to the transmission side of the lens. Last piece of the puzzle. Suppose I have an application that needs a particular focal length. Just hypothetically. An application that needs a particular focal length so that the image for an object that is far away ends up at a very particular place on my retina. How do I engineer a lens to do that? Because the lens has two phases. And the trouble is, one of the sides is, it's a glasses lens. One side is convex, has an outer curvature. The other side is concave. It curves in. So how do we determine what, is it diverging or converging? And the answer is it depends. And we can use the thin lens, the lens maker. So that's what we're trying to do, the lens maker equation. One over F n minus 1. 1 over R1 plus 1 over R2. And again, this is just geometry. If you want to prove it, we can. I'm kind of approaching it from a let's not say we did standpoint at this point. But if you want to, let me know. We can prove it. The only trick here if you look up the lens maker equation, you might find with a plus sign here, you might find with a minus sign here. Both are correct. It's just a matter of which sign convention we're talking about. We're coming from the object side. A convex surface uses a positive radius. A concave surface uses a negative radius. The left surface for a lens like this is convex. It bubbles out. The right surface is concave. It bubbles in. A double convex would look like this. And that would be positive plus 1 over positive. This one is 1 over positive plus 1 over negative because the other surface is concave. If we had two concave surfaces, we could do that too. Both of them would be negative. The lens maker equation, and with that, we are done. Thanks, everyone.